you don't have questions for me. I don't get it anymore. I'm not understanding. I looked at how much of you are doing the study plan. It's like half the class has done a quarter of the work. So, all right, this is homework 26. And it's number 12. Number 12, is that right? No, I don't think there are 12 problems in homework. Oh, yeah, there is, yes. Question 12. And I want to graph y equals negative 3 sine of negative 2x plus pi over 2. So I want to get this in the form that I taught it to you. I want to factor out that b, right? So I'm going to factor out that negative 2. And I'm going to have x minus pi over 4 left over. And if I distribute, it's easy. Right? Distributing that, I clearly see it. So it's also pretty clear you just doubled it. If I factor out a 2 from the numerator, you double your denominator. If I factor out a 3 from the numerator, you triple your denominator, etc. Right? So now I can clearly identify the mother, y equals sine of x. I can clearly identify the reflection, y equals negative sine of x. And I can clearly get the amplitude, um, 3, right? Or y equals negative 3 sine of x. So it's nice to at least show this. I don't think I asked for this on the test, but if you showed it to me, I'd be very happy. So I want to be able to see all 3 of those, the mother, the daughter, the granddaughter there, right? I need quarter steps. I need the original rectangle for the mother, and I need the rectangle for the granddaughter. I think you can see the colors there, I'm not sure. Make it a little bit clearer. So the mother in black for sine is 0 to 1 to 0 to negative 1 to 0. Right? So there's the mother function y equals sine of x. The reflection just takes all of the positives and makes them negative, or all of the negatives and makes them positive. So there's y equals minus sine of x. And then finally, when I put in that amplitude, I'm saying change the radius, change the diameter, right? So so now I'm going, right, using those same, right, almost smooth. So there's the granddaughter. And of course, all 3 of those on the same curve on your calculator is pretty easy to see, right? Where it gets weird is when we find a frequency here. And I'm giving you a positive frequency. This one's got a negative frequency. What's the difference? When it's a positive frequency, I'm going counterclockwise. When it's a negative frequency, I'm going clockwise, right? So my frequency here is b equals negative 2. What is that going to do, right? So I would like to look at y equals sine of x and y equals sine of negative 2x, because it will clear up what's really happening there. So sine x is got a period of 2 pi, right? And I'm working counterclockwise, so I'm working right to quadrant 1 to quadrant 2 to quadrant 3 to quadrant 4. So there's my y equals sine x again. And you'll see I have to do a quick sketch like that a lot today with the new material. Now, So positive says build my rectangle to the right for frequency. Negative says move it to the left. So, and instead of my quarter steps being pi over 2, they become pi over 4, right? So I'm building this guy now. And so I need new quarter steps here. So there's y equals sine of negative 2x. And again, easy to see on your calculator, right? So you want to play around with these. Play around with the different aspects of A, B, C, and D. Plus or minus A, B, C, and D, right? And this guy, y equals plus or minus trig A times trig of B times quantity x plus C all plus D, right? And I'm only giving you sine and cosine for the test. You'll use tangent quite a bit in Calc 1, so you should be comfortable with the tangent curve as well. But I'm not testing on it.
So I'm not. I don't think it's quite clear to me what the frequency does. Could you explain it again?
Sure. So frequency is the number of times the curve is repeated inside of 2 pi. So if I look at just my plain old sine x curve, right? This is got a frequency of 1. So y equals sine of 1x says repeat the curve once. Once in the period of 2 pi. When I say y equals sine 2x, and again, you should look at sine 1x, sine 2x, sine 3x, sine 4x from 0 to 2 pi. You should be experimenting with this. Play around with the values of A. Play around with the values of B. Play around with the values of C. If you do it on Desmos, you get a nice, you can do the sliders, right? And we're talking about getting understanding here, right? We're talking about sitting there and doing experiments, mathematical experiments. So, first of all, I want to look at 0 to 2 pi for my x-axis. So 0 to 2 times pi. Excuse me. And I like quarter steps of pi over 2, right? My y-axis, it's because I know it's max 1, min minus 1. I can, I'll just go negative 2 to 2. So there's a pretty good grid. Oh, did I go negative 2 to 1? It doesn't matter. I'm just going to drag it with my finger here. And I want to see that 2 pi. So I'm going to graph y equals sine of bx. And I'm going to make b a slider. So there's b as 1, right? And I guess I should put the mother on there, y equals sine x, right? No slider involved, right? When I make b2, you can see, I can see the sine curve twice. That's frequency. How often does something happen? If I make b4, I can see the sine curve 4 times now, right? You're looking for that.
Okay. So does it like kind of compress it like sideways?
Yeah. Yes. You remember when you're multiplying x's by 4, it actually means you're crushing the curve down to 1/4 because x's behave inversely. So, for example, if I let b be a half, positive 0.5, You can see I only see the first half of the sine curve in red.
Okay, that makes sense now.
And if I go out to 4 pi, now you can see in red, you can see the whole sine curve. Right? In red, you can see the whole sine curve because it says inside of 2 pi, just do half of the curve. So that means inside of 4 pi, you do the whole thing, right? And remember, that's going to come from the frequency, the period, right? It says the period is 2 pi over b, right? So when b is 2, I get 2 pi over 2, it does the whole curve inside of pi. That means when I get to 2 pi, I've got the curve twice. If I do y equals sine of x over 2, now b is 1/2, right? So 2 pi over 1/2 is 4 pi. It takes 4 pi time to get the whole curve, so it's stretched, right? Stretched out, not compressed. Okay, back to our problem. And remember, I asked you to kind of see if you could make that same thing I did on Sketchpad on Desmos. Anybody try that yet? Don't even answer. But if I open my Sketchpad version of it, I'm just trying to emphasize the most difficult part of this particular problem, which is when b is negative, my rectangle moves the other way, right? So I got just my mother function and this transformed one just slightly off so you can see them both. But I'll make b negative now. And you can see, so as I get closer to 0, between 0 and 1, it's stretching it out. And then as soon as I get negative, you can see my rectangle's moved the other way around the circle. Okay, back to our problem. Sorry, Alejandro, I'm just reading. Yeah, which points are you talking about, though? Oh, the quarter steps. Yes. Well, when it's just the mother is just they're pi over 2s, right? So the period for the mother is 2 pi, right? So quarter steps are 2 pi over 4, so pi over 2s. So this is 0 pi over 2. This is 1 pi over 2. 2 pi over 2. 2 pi over 2 is pi, halfway. 3 pi over 2 and 4 pi over 2. 4 pi over 2 is 2 pi. Right? We're talking about over here, right, where the period is pi. So the quarter step would be pi over 4. So I have that one. Where do I have that one? I didn't do that one yet. Sorry. So if I let me just do it over real quick. Right? Y equals sine of x. Let me get a new page. Sorry. So y equals sine of x, right, is 1, 2, 3, 4, up to 1, down to -1, right? And that rectangle for the mother, right? And so, so there's my sine curve. I should be able to draw. You should be able to draw it as fast as I do. And we know it starts at 0 and ends at 2 pi, right? The middle is pi, of course. So, but if I give you the curve y equals sine 2x, right? Now the period is pi, and the quarter step is pi over 4. So I need to cut pi into 4, right? So I cut pi into 4. And there's my new box. And there's my compressed sine curve. And you can see it can happen twice inside of the original unit circle. What do you think? That okay? That clear it up?
Professor, I have a question.
Yes, Grace.
So the formula for getting the period is 2 pi over b?
Correct.
Wasn't our b -2?
Yeah, I'm not there yet. I was answering
okay.
a question in the chat. Yeah. So I'm ready to do that whole problem now, because I did a bunch of pieces of it, right? I did the mother, I did the reflection, I did the amplitude. I started talking about, I did do the -2, right? If you could see it here. Sorry, it's up here. There's that, right? There's that great granddaughter. Right? Remember I said B is positive, we're working to the right or counterclockwise in the circle, and if B is negative, we're working left or clockwise on the circle. So, but I think we're ready for the whole thing now. So y equals -3 times the sine of -2 times, excuse me, x minus what was it again? Pi over 4?
Yes.
Yeah. Nice. So I got amplitude, I'll just say -3, even though it's just 3, right? But I know I need the reflection. I've got B is -2. I've got the period is 2 pi over -2. So it's -pi. So I want to move the rectangle that way, right? To the left. I get my quarter step. And this is exactly what I want on the test. Okay? Exactly what I want, everything like this, just on the test. A quarter step is minus pi over 4. So every time I move left, I'm moving 1 pi over 4, then 2 pi over 4, then 3 pi over 4, then 4 pi over 4. My start is my phase shift. I'm going to start at pi over 4. Remember, I'm asking, what x makes that piece 0? So I'm starting at pi over 4, and then I want to start to think about, take the first step, right? So what am I going to do? I'm going to take my start and add the quarter step. So I go to 0 pi over 4. All right, that's kind of easy, right? Because I can see my start and steps come from pi over 4 to 0 pi over 4 to minus 1 pi over 4, minus 2 pi over 4, minus 3 pi over 4. Right? Nice little sequence there. Arithmetic, of course, because I'm adding the same thing every time, minus pi over 4. I'm adding the quarter step every time. The one I gave you on your test, you will have to convert to common denominators, right? Just like I've done in class a couple times. So, I'm ready to graph it. I might as well look at the mother at the same time. So for the mother, I know I need 1, 2, 3, 4 quarter steps. Kind of the mother, I'll look at kind of the mother. I guess I don't really need to. But I know I need to go up 3 and down 3. And I need to move from 0 to minus pi. But I need quarter steps of minus pi over, minus pi over 4. So I'm looking at this rectangle now. Now I want to put on the right hand side, and you don't have to do this, but just so I can emphasize at y equals negative 3 sine x, right, that I'm emphasizing that I have this shape, for, right, so that I can see that it has to continue that same shape, but I'm compressed, right? Sorry, down here. Right, so I can see that quick one and the slower one. So the red is my original function, y equals negative 3 times the sine of negative 2x plus pi over 2. And that was the original problem. Sean, what do you think?
Yeah, I think how'd you get the period again?
2 pi over b.
Oh, like how'd you get it?
Take 2 pi, divide by the b value.
Oh, okay.
Right,
okay.
b is negative 2, right?
And to get the quarter steps, you need to divide your period by 4?
By 4, yep. To get a quarter.
And that's how. Okay.
To get
those are your tick marks.
Exactly.
Okay.
And I would want those on there, right? I would want minus pi over 4, minus 2 pi over 4, minus 3 pi over 4, minus 4 pi over 4. Right, and you're really only showing, you know, that piece of it. I don't care about this other stuff. Right? This is 0 pi over 4. Oh, I made a mistake, didn't I? I'm supposed to start at 1 pi over 4. Sorry about that. Silly Robert. So I'm supposed to start, so here are my tick marks. Sorry. Let me do a brand new page. Let me show all the way to 2 pi, all the way to minus 2 pi, right? And I know I'm starting at minus pi over 4 and ending at, right, I'm ending here. And again, I like to draw my curve left to right. There it is, sorry. Y equals minus 3 times the sine of negative 2x plus pi over 2. And I can see that my ticks are labeled, right, just the way I found them. Start was pi over 4. First step went to 0 pi over 4. Second step went to negative 1 pi over 4. Third step went to negative 2 pi over 4. And I ended at negative 3 pi over 4. Right? That's what I had for my start and step sequence. Right? I had pi over 4, 0 pi over 4. Minus 1 pi over 4, minus 2 pi over 4, minus 3 pi over 4. Sorry about that.
So just to be clear, when you get the quarter steps, what you do is you get the phase shift and you subtract it by itself.
So once I get the start, the phase shift, I add the first step, right? Which in this case would have been minus pi over 4, right?
So you add them.
Yeah. So remember, my start was pi over 4. My first step is pi over 4 plus the quarter step, right? And the quarter step we figured out was minus pi over 4, right? So pi over 4 minus pi over 4, that gave me my first step at 0. So when I took my first step right there, I went to 0. I started at pi over 4, took my first step, went to 0 pi over 4, went to minus pi over 4, minus 2 pi over 4, minus 3 pi over 4.
Professor?
Yes, Grace.
So will the curve always start with moving upwards to the next step? Or are there situations in which it would move downwards?
Yeah, so this one actually moves downward. If you see, because I started, I'm always trying to draw left to right. If I'm drawing left to right and there's no reflection, it's that standard sine curve, right? So this is y equals sine x, right? And then if it's starting the other way, meaning starting down, it's y equals negative sine x. Again, you can just think, you can see if this is positive 1, right? This is pi over 2 comma 1. This point right down here is pi over 2 comma negative 1, right? Because that negative on the outside is changing the y values.
But I thought we were starting from positive pi over 4.
Good, but b is negative. When b is negative, my rectangle works that way. It works the opposite direction.
Okay.
I am not giving you a negative b value on the test. You're going to have a positive b value on your test. Cool. I'm ready to... Oh, sorry. Go ahead, Sean.
Yeah, so if it was positive, we would move it to the right, I guess? Or
yes.
This is negative,
yes,
right?
Yes, exactly.
Okay.
Alejandro, I don't teach the way MathXL teaches. So when MathXL asks you a question, you can go their way if you want to, which I think is more complicated, right? MathXL would not have you factor out this. MathXL, or the book, I'll say, taught you to do this without factoring out the b value. And I don't teach that way because the notation is nasty. So I say factor out that b value and do the process the way I taught you. I don't care which way you do it, as long as it's right and as long as you can give me everything I asked for, right? No, you don't have to do it their way. You don't have to do it my way. You just have to do it correctly, right? So do it any way you want. I think the way, and believe me, this is something that students have been struggling with forever. And so I'm just trying to simplify it as much as I can to just think about A. Just think about B. Just think about the period. Just think about the quarter step. Think about the start. Think about the first step. Think about all the steps. Draw the rectangle. Draw the curve. Right? It's pretty much, I'm trying to break it down into very, very simple steps. Right? Walking to California is not easy, but every single step is. Okay? And that's how I'm trying to always teach. I'm trying to say, let me do one little tiny thing so that I don't screw anything up, right? If you think about the whole thing, oh my God, it's overwhelming. And this is true about the rest of your life in mathematics. Nothing we do is difficult. Remembering what to do is difficult. So, same for brushing your teeth. Do it enough, it gets very easy. You have to practice. You have to explore. You have to investigate. Desmos lets you do it. I used to use a program called Derive. I would have to go to school to do it because it was an expensive piece of software. I had to go to school, go to the computer lab, play around with the functions. Then I eventually got a graphing calculator, a Hewlett-Packard reverse Polish graphing calculator. And then I could start to experiment and play around with curves. What happens if I change this? What happens if I change that? Right? So that you kind of build up this knowledge of functions in your head so that when you arrive at one, you don't need the calculator anymore. So when you hear a song, you can just play it. You don't need the music. You don't need someone to tell you what to do. You can tell what, you can hear it. You've practiced so much, right? That you've built up this relationship, this mastery of material. That's what you're trying to do. It's about practice, right? And for us, we said, okay, we're meeting in class 5 hours a week. So we're talking about 10 to 15 hours of work in addition, right? So talking about 20 hours of time just on this one course. And yes, it's your job. Right now, it's your job. It's your job to prepare you for your real job when you're making $100,000 a year, right? When you're changing a city, when you're changing the universe, when you're changing a medical field, right? All right, let's do new stuff. So we're going to do chapter. We're doing solving trig equations today. It's a little heavy. It's okay. Just make sure you go back and watch the video after your test and get to work. Anybody any success with the trig identities over the weekend? Anybody try any trig identities?
A little bit.
And
No, I didn't.
any success?
I struggled for about 20 minutes and then I gave up for the weekend, to be perfectly honest.
Yep. You got to get in there and you got to play around with them, right? Is there one you want me to do? Diego or Joe?
Not one in particular.
Let's do one real quick. I'm going to grab it. Remember, I did not assign a homework. I did not create a homework. By the way, I finished the homework 7. All of chapter 7 is done. There are 10 problems each. You got to wait for me really to teach it. You should be able to do 7.3 after today. But 7.4 doesn't exist because just do the ones in the book. Okay? So I'm going to pick one here from 7.4. And in 7.5 and 7.6, these trig identities will keep happening. So make sure you keep doing them. I will put 2 or 3 on the next test. I will put definitely 1 or 2 on the final. Where the heck is this section? Where is this stupid section? Oh, I'm in 7.1. How did I do that? Sorry, I'm looking at my other monitor here. I'm just going to go find a problem real quick. So if you remember, I liked questions like 45 to 93, right? 45 to 93. Let's do 77. So I've got the secant of theta divided by the quantity 1 minus sine of theta should equal 1 plus sine theta all over, does that say cos cubed? Really? How do I zoom in on this stupid book?
Yes, it says cos cubed.
It says cos cubed, thank you. Nice. Well, I definitely am thinking that the right-hand side is more complicated, even though the left-hand side has a secant. But I'm going right-hand side, just my gut, right? So 1 plus sine over cos cubed, right? Remember, I'm doing this without, I don't want to write too much. I'm a very lazy man. Sometimes I sit down on the sofa and I forget to get the remote control, so I just sit there and watch TV anyway with it off. So 1 plus sine all over cos cubed. It's looking like a conjugate to me. Why am I thinking that?
Is the 1 plus sign?
1 plus a trig. When I see a 1 plus a trig or 1 minus a trig, I'm thinking conjugate. This one, it turns out I don't think I have to do it. But so let's see if I can think of what I can do downstairs. Well, it looks like I do cos times cos squared, right? Cos times cos squared. And I do have, when I see a trig squared, or 1 plus or minus a trig squared, I'm thinking Pythagoreans. What's my identity for cos squared? Remember sine squared theta.
Plus sine squared?
Nice, 1 minus. Yeah, 1 minus.
Minus.
So I get 1 minus sine squared there. That happens to be factorable, right? Remember, a squared minus b squared is a plus b. Remember from 8th grade or whatever grade we learned that stupid difference of squares factoring a plus b times a minus b, right? And this always shows up when we use conjugates, right? So I see here I've got 1 plus sine upstairs. I'm wrapping it now because I'm going to see it cancels. And I have a 1 plus sine downstairs and a 1 minus sine downstairs, right? You with me? 1 minus sine squared factors into 1 plus sine, 1 minus sine. And so it looks like my 1 plus signs will cancel. And I see that I have 1 over cos times 1 minus sine. Wow, that looks really familiar to it looks really close to my left-hand side. What's my last secret here is to move that cosine up to become a secant. Check.
But how did you move the cosine up? Like you just
1 over cosine of theta is secant of theta, right? That's a reciprocal identity.
Oh, okay.
Right?
Oh yeah, true. Yeah, I got it.
We do a lot of these in calc. A lot. You want to be a master at doing these. You want to practice all of them. Do all of them. How many students?
Sorry, Professor,
yes.
Could you explain how you went from 1 over cosine 1 minus sine to secant?
Yeah, right here. The secret is the reciprocal identities. 1 over cosine is secant.
You're right.
Yeah. Let's see, 4.
Can we do another one?
Sure, pick one. 4, 8, 12, 16, 19 students. Holy, what happened? How could I have 19 students here? That's awesome. And the one student out here sent me an email. So thank you for doing that.
Let's do 87.
87, good pick. I have no idea what it is, but any question is a good question. 87. Looks nasty, huh? I'm going to change my comment of good pick, but it's fine. 2 cos squared of theta minus 1 quantity squared, right? Is 87, right? All over 1 minus 2 cos squared theta, yuck, equals secant of theta minus sine of theta all over the quantity tan theta minus 1. Wow. Well, I can say for sure I'm thinking left-hand side is more complicated, right? I can already tell you that this feels like one where I'm not going to get there working one side only. And this is just from years and years of doing these things and practicing. I'm telling you, when I was a student, when I was in pre-cal like you are right now, I did every problem.
No, Professor, I think you merged 2 questions.
Thank you. I was going to say, it looks horrible.
Yeah.
And remember, when you try it 5 times and it still doesn't work, oh, yes, thank you. Right-hand side is 1 minus 2 sine squared theta. Be careful of that. You will copy.
Oh my God.
You will copy things down wrong a lot. Is the left-hand side look right? Somebody help me because I'm looking
also, on the left-hand side, the denominator is cos to the power of 4
Oh my
minus.
god. Oh my god.
Fantastic.
I'm sorry. I mixed 3 problems. Cos to the 4th minus sine to the 4th. Thank you.
Yeah.
Thank you for saving me a lot of aggravation there. Perfect. I still think I'm going to be stuck here. It's kind of hard to see on the right-hand side what I would possibly do. And definitely the left-hand side looks more complicated, so that's where I'm going, right? So on the left-hand side, I got 2c squared minus 1 quantity squared over c to the 4th minus s to the 4th. So much quicker to do these this way. Well, upstairs, it looks like I can FOIL, right? Downstairs, it looks like I can factor. So I don't know what to do yet. I'm going to just try and leave the upstairs alone first. I'd rather factor than distribute, okay? So downstairs, I get a c squared plus sine squared, c squared plus s squared times c squared minus s squared. Oh, look at cos squared plus sine squared. What's that?
1.
1. So I get 2c squared minus 1 quantity squared over c squared minus s squared. I have a feeling that since I have cos squareds upstairs, I'd like to have only cosines downstairs. Just a gut, right? But remember also when I see a trig squared, I'm thinking Pythagorean. So what can I do downstairs here with my sine squared? What can I put in there?
Sine squared is equal to 1 minus cosine squared.
Nice. And now, again, I'm interested in factoring, but I can't have these random terms and parentheses, so I got to get rid of this. So I get c squared minus 1 plus c squared. Oh, sorry, that's downstairs. Sorry. So excited to see what to do. I'm skipping writing the numerator. So I get c squared minus 1 plus c squared.
Professor?
Yes, Grace.
Oh, sorry, I got lost in the denominator.
Yeah, let me give numbers here so we can make sure that I'm in the right place here for you. 5 to 6, 4 to 5, right?
Yes.
4 to 5. Good. So notice everything in black is the same from 4 to 5. And what did I change? I took this sine squared and changed it into 1 minus cos squared. Why? Because my gut is saying if I've got cosines upstairs, I'm not going to be able to cancel them with sines downstairs. So turn everything into cosines, right? You see it, Grace?
Yes, thank you.
Nice. So downstairs simplifies now. I get 2c squared minus 1 quantity squared over 2c squared minus 1. Oh, what do you know? So right, remember I said I could FOIL upstairs, but it looks a lot better. Wait a minute, what happened? 4, 8, 12, 16. Oh, now I have 19 students. Welcome, Rafat. Good morning. Now I have 19 students. All right, so upstairs you can see I've got 2c squared. What's that, Rafat? So one of those factors cancels. So it really is a good idea to not distribute. You're trying to factor more often. And that's going to happen a lot in Calc 1 too.
Professor?
Yes?
I'm a little bit confused from how you got from 3 to 4.
So 3 to 4, I just used...
In the denominator.
Yeah, I've got an a squared minus b squared. Turns into an a plus b times an a minus b, right? But since I have a to the 4th minus b to the 4th, that's going to turn into a squared plus b squared times a squared minus b squared.
Okay. All right, and then.
Go ahead, I'm listening.
Sorry,
I don't mind.
Because if you like FOIL out.
Yeah, we're trying to not FOIL, right? It is a 4-letter F word, right? So we're trying not to do that. We're going to try and factor.
Okay.
Okay. So look at what I have. I'm so close. I have 2c squared minus 1 equals 1 minus 2s squared, right? But remember, I'm still working on the left-hand side here. Do you have an idea what to do? Anybody?
We could turn it into 1 minus the c squared into 1 minus s squared.
Nice. So I've got a 1 minus sine squared now, and you can really see it's done at this point. So I got 2 minus 2 sine squared minus 1. So I get 1 minus 2 sine squared, check. This is a good one to do. Possibly try it on the right-hand side. It's very difficult to take something so simple and make it complicated, right? But certainly you could try it. Now that you did one side, it kind of gives you hints at how to start on the other side. All right, let's do 7.3. So we're solving trig equations. And I'm going to pull out all the tricks, okay? I'm going to pull out all the tricks. I'm going to be thinking about the reference table. I'm going to be thinking about the bow ties. I'm going to be thinking about the sine. I'm going to be thinking about all the curve, the original mothers of sine or cosine. And I'm going to be thinking about quadrants. All students take calculus. And I'm going to be thinking about sequences and series. Everything is in this, okay? And this is essential to your calculus, right? Essential to the calculus that you're going to be doing next semester. So I want to start, I will give us a little, step-by-step thing happening. But I want to start with something nice and simple here first, okay? So I'm just opening the chapter, section 7.3, solving trig equations. Now, solving trig equations keeps happening every section. So this is 7.3, so it happens again in 7.5, it happens again in 7.6, okay? And I want to just look at kind of what are the 3 types of equations I'm going to solve. So my 3 types are single trig equations. So it will only have a sine in it or a cosine or a tangent in it. I'm looking at trig equations with identities. And then finally, trigs in quadratic form. So in this one, we're going to be trying to factor, right? In this one, we're probably going quadratic formula. Of course, you could factor that too, but it's a lot easier, a lot quicker just to go right to quadratic formula. So we want to look at something like cosine of theta is 1/2. So this is a single trig, right? So we're saying solve for theta. Okay? Yes, you with me? Good. I should already know what my reference angle is. When is cos of theta equal to 1/2? Pi over what?
Over 4.
No.
I think it...
Who left? Who left? Damn it. Now I gotta take attendance. Every time you come in, someone comes in or someone leaves, I take attendance. And when I go put my attendance in the book, I use my last photo. So, yeah. If you miss more than 4 classes, I can drop you from the class. All of the students that are missing more than 4 classes are failing. I don't bother dropping you from the class because it's paperwork for me. I don't feel like doing it. But if you're going to be successful in mathematics, engineering, etc., science, you better go to class. Go to class. Or figure out some other way. If you don't want to go to class, figure out some other way because it's not working. It's not working. If you're missing class and failing classes, it's not working for you. Okay? So you got to get serious. Get serious or get the hell out. That's the theme. And that happened to me. I started right after high school and I hated it. So I dropped out. 7 years later, I'm still broke. Right? Go back to school and give in. Be serious. Right? And then 5.5 years later, I finally got my bachelor's, started working, and started making money. All right, reference angles. Who said it?
Pi over 3.
Thank you. So I want to be thinking of cut pi into 3, right? Cut pi into 3, or the whole circle into 6, right? And I know that cosine is positive in quadrant 1 and 4, right? So I already know the angles that I'm going to get this from are going to be pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. And in fact, if I keep going, I'm going to get more answers, right? So I should think of the cosine curve. It's nice for me to be able to think of this cosine curve of when am I going to get positive values, right? So I'm going to get so this is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4, and if I could see my positive 1/2, right? And I draw that horizontal line over, oops. I missed on the first curve. If I draw my positive 1/2 over, oops, I missed on the second trial too, sorry. Try and be a little bit more precise, Robert. You can see I hit a solution. I hit the height. Cosine equals a height of 1/2 in quadrant 1 and quadrant 4. That's why I drew, right, my bow ties. And I'm really emphasizing this triangle and this triangle, right? Those are my 2 triangles I need, right, to get a positive 1/2 out of cosine. Now, if I think about it, this thing gives me another answer every time I go around a circle, right? Every time I go around a circle. So I'm going to get my answers for theta. So theta sub 1 is pi over 3 plus 2k pi. The 2k pi is every time around a circle. So when k is 1, I go around a circle. When k is 2, I go around a circle again. When k is 3, I go around a circle again, right? And my other answer, theta 2, is 5 pi over 3 plus 2k pi. Now, I wonder if I can get a nicer answer out of this, right? And so this is where my sequences and series come in. I wonder if I can have my answer come from just one formula. So what I do is I write out a sequence of solutions from each result, right? So from theta 1, oops, not Q, theta 1, I get my first answer is pi over 3. My second answer, right, is pi over 3 plus 2 pi. My next answer is pi over 3 plus 3 pi. Sorry, 4 pi. Remember, I'm doing 2k pi. So 2 times 1 times pi, 2 times 2 times pi, 2 times 3 times pi. I think that's enough. I think 3 should be enough. But I want to simplify that. So I get pi over 3 plus what? 7 pi over 3? And now I know the next one is 11 pi over 3. I don't have to think, right? Because once I see the pattern starting, right? Once I see the pattern starting and knowing I'm adding the same thing over and over, I don't have to think about this, right? So theta 2, I want to, oops, why do I keep writing Q? I'm not a QAnon person. Theta 2, oh, I started watching the Squid Game. Wow, how screwed up is that? Is it? Oh,
no,
God.
Professor!
It's so screwed up.
No, it's trash. Don't watch it.
It's better in Korean. Better if you watch it in Korean.
Don't give
Professor's a
in
weeb.
to
Keep
society's
No,
demands.
don't listen, Professor. Keep watching it.
No.
I have to watch it now. I have to.
It's amazing.
Once you get sucked into the squid tentacles. I don't know why there's 8 of them and they call them tentacles. They should be
Octopus.
octacles, yeah.
Well, I think tentacles just refers to any of them.
It's a
They
joke.
don't have a specific number.
Yeah, I'm not trying to be tentacle about it.
That's fine.
Technical about it, yeah. It's just a
I
joke.
hate this
Alex.
class.
All right, all
Someone
right. 5 pi over 3. Anyone guess the next one without me doing any work? Oh, I made a mistake. 7 pi over 3. That should be 13 pi over 3. Anybody guess what this one is? All right, fine, we'll do it. So 5 pi over 3 plus
11
2.
pi?
Yes, 11 pi, exactly. So I get 5 pi over 3, and then what is that? 6? Yeah, 11. So I already knew what that next thing would be. I'd have to add 6, right? So 17 pi over 3. Okay, so now I'm looking at theta, right, as pi over 3, 5 pi over 3. I'm taking them in order. 7 pi over 3, 11 pi over 3, 13 pi over 3, 17 pi over 3, and I'm wondering, is there a formula for this? Right? Can I come up with a formula for this? Well, if I could, with my current knowledge of sequence and series, I'd have to be arithmetic, right? And so I'm asking, am I adding the same thing to get the next term? Am I adding the same thing as I get to get the next term?
No.
No. So done. So this is no good to me. So this is my actual final answer. So I want to write out my individual answers, right? Write out some terms, create a series from it, and see if I can come up with a formula, an nth term for that. If I can't, then I have to use my piecewise solution, right? If I can't come up with one formula to find the solution, I have to come up with, I have to use my piecemeal solution. How we doing?
It's a lot.
You ain't seen nothing yet. Here we go.
We
I'm
ain't seen
aware.
nothing yet.
Not seen nothing yet. This is the easiest problem.
This is the easiest
Oh, boy.
one, yeah.
This is the first one. This is the easiest problem.
One you can solve off the top of your head, sure.
Sure. So let's do another one. So sine squared theta equals 1/4. So single trig, right? Single trig, just what we want, right? And so I'm trying to solve for theta. So if I have a sine squared, I want to get to a sine, and then think about the reference table, the sine graph, the bow ties, right? So what do I know? I know that sine of theta is plus or minus square root of 1/4, right? So sine of theta is plus or minus 1/2. All right, that's nice because we know that the sine, right, is doing this, right? And we know we hit a plus 1/2 in 2 quadrants, and we hit a minus 1/2 in 2 quadrants. So we hit a plus or minus 1/2 in all 4 quadrants. So we know we're going to be using 4 triangles, but what's our reference angle? When is sine 1/2?
Pi over 6.
Nice. So we want to cut pi into 6, or the whole circle into 12, and look at those bow ties. But we know we're going to use all 4 of them, right? So we're going to use pi over 6. We're going to use 2, 3, 4, 5 pi over 6, 6, 7 pi over 6, 8, 9, 10, 11 pi over 6.
Professor,
Yes.
I'm missing something. How did the reference angle come to pi over 6?
I use my table. So sine theta, so 0, pi over 6, pi over 4, pi over 3, pi over 2. Right? And I have square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. And so there's my reference angle. When is sine 1/2? When theta is pi over 6.
Thank you.
You're welcome. So I can see possibly, right, that I might have a nice nth term here. It looks like it's possible. I certainly can think of theta 1 as pi over 6 plus k pi. That's kind of nice because, right, this is halfway around a circle. So pi over 6 plus k pi will get me another answer, plus another pi will get me another answer, plus another pi will get me another answer. And then I can do the same with pi theta squared. I can do 5 pi over 6 plus k pi. Right, took my first answer, added, added pi to get my third answer. Took my second answer, added pi to get my fourth answer. And then that pattern keeps going. But it would be nice if I could see a single formula for theta. And remember, k belongs to the integers, right? Which is dot, 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 -2, -1, 0, 1, 2, dot, 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 right? So either going around a circle either way, right? So I want to check this if there's a possible formula for everything. It turns out that there's not. So I can see that theta would be 1 pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6, right? Etc. But I can already see that I'm not adding the same thing. So this guy's really no good for me, and here's my answer. So there are a few that will generate a beautiful series or nth term, and I will put one on your test for sure, okay? Because I want to recap that chapter 12 stuff we did, right? If I can put this chapter 12 stuff here in this section, I don't have to put both on the final, right? So let's do one more like this, and then we'll look at one more of each of the other types of problems. So cos squared theta equals 1/2. This is going to give me a nice, let me write that over, sorry. So cos squared theta equals 1/2. So I want to solve for cos first of all, right? So cos of theta is plus or minus square root of 1/2, which of course is, if I rationalize, rad 2 over 2. Reference angle is what?
Pi over 4.
Yep. So I know I'm talking about cutting pi into 4 or the whole circle into 8. And I know I'm going to use all 4 of them because cos is either plus or minus rad 2 over 2 in each of these, right? So I don't really need the quadrants. I already see I'm going to hit a positive 1/2 here and here. I'm going to hit a negative 1/2 here and here, right? You can see those quadrants happening. And this is a positive 1/2. This is a negative 1/2. And I'm just going over with a horizontal line, and I see where I'm hitting the curve. So you can see I'm hitting the curve in every quadrant. So every piece of the bow tie I need. So I'm talking about pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. But on this one, I can already see that I'm adding 2 every time. I'm adding 2 pi over 4 every time. So I actually get, for theta, right, I get 1 pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, etc. And I can see that I'm just adding some multiple of 2 pi over 4, and I can get that answer by pi over 4 plus k times 2 pi over 4, right? I'm adding 2 pi over 4 every time. So I get a nice answer for theta of pi over 4 plus k times pi over 2. And there is my answer. You see, that one turns out to be very nice. Notice when k is 0, theta equals pi over 4, right? 0 times pi over 2 cancels. When k equals 1, I get theta equals pi over 4 plus pi over 2, which of course is 3 pi over 4.
Over 4.
Yeah, and you see I'm just going to generate now. When k is 2, I get theta equals pi over 4 plus 2 pi over 2, which is just pi, so I get 5 pi over 4, etc. I don't need to keep going. Right? We can already see it's generating all of those values for me. So our ultimate goal is to have a single solution for theta, but if I have to have a piecemeal one, theta 1 and theta 2, that's fine. All right, let's look at...
Is there a reason why you particularly multiply k times 2 pi? Or
So I went back to chapter 12, and I figured out that I was adding the same thing every time. So I knew it was arithmetic, right? So I came up with an nth term, kth term, right? In chapter 12, we would have said theta equals pi over 4 plus n pi over 2. But I'm just, for some reason, we use the value k now. Good, let's look at one that's a little bit more complicated. I think we're only going to have time to look at this, not probably finish it, but let's see what happens. So I got 2 sine squared theta minus 3 sine theta plus 1 equals 0. Well, it's quadratic, obviously. X squared, right? You can really see the 2x squared minus 3x plus 1, right? So we want to solve this with quadratic formula. So x equals minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. So I get 3 plus or minus 9 minus 8 all over 4. Nice. 3 plus or minus square root of 1 over 4. 3 plus or minus 1 all over 4. So I get two answers here. X equals 3 plus 1 over 4, or x equals 3 minus 1 over 4. So I get x equals 4 over 4, or x equals 2 over 4. So I get, and remember what x is, it's sine. So I get sine of x equals 1, or sine of x, sine of theta, or sine of theta is 1/2. Beautiful. Sine of theta is 1 is pretty easy. It only happens at pi over 2, right? So theta 1 answer is pi over 2 plus 2k pi, right? Because it's going to happen every time I go around a circle, right? It's going to happen again here and here, etc. And right, and the period is 2 pi, right? So I'm adding 2 pi. Go ahead.
So for any of these quadratics, like you can just substitute the trig for x and go from there, and then plug it back in afterwards.
Yep. And then from my other answer, sine equals 1/2, right? I know I'm going to get an answer in quadrant 1 and 2, right? I'm going to get a height of 1/2 in quadrant 1 and 2, and my reference angle is pi over 6, right? So I'm going to get in quadrant 1 and 2, I'm going to get pi over 6, 2, 3, 4, 5 pi over 6. So theta 2 is pi over 6 plus 2k pi. Theta 3 is pi over 6 plus 2k pi. And this 2k pi thing is a little confusing when you first learn it. But you'll be fine. You'll figure it out. And there it is. There are all my answers. So theta is the set of pi over 2 plus 2k pi, pi over 6. Oh, that's a 5 pi over 6. Pi over 6 plus 2k pi, and 5 pi over 6 plus 2k pi. That one doesn't get nice. There's only a few. There's only a few, and I'll do them all before test 4. There's only a few of these that takes a theta 1, a theta 2, a theta 3, etc., and turns it in just to a theta. Right? So there's a lot of these don't make a nice pattern together. This one does not. I guess one more. Why not? Wednesday we're just going to review, right? No, I really don't like these problems they have in here. Oh, here's one, number 59. So I've got 2 cos... No. Oh, yeah. 2 cos squared theta plus cos theta equals 0. So this kind of looks like a quadratic. In fact, I could do it as a quadratic, but it's easier to factor this way. So I'm going to factor out a cos theta, and I get 2 cos theta plus 1, all equals 0. So I get cos theta equals 0, or 2 cos theta plus 1 equals 0. Oh, so I get cos theta equals 0, or cos theta equals minus 1/2. The answers that I'm going to give you will always be on the reference chart. So is there a 0 in the column for cosine? Yes. Is there a 1/2 in the column for, is there a 1/2 in the column for cosine? Yes. So for the first one, cos of theta equals 0, right? Where is it happening? It's happening at pi over 2, 3 pi over 2, right, etc. So it's happening at odd pi over 2, so theta equals 2k minus 1 pi over 2s. Right? We figured out that odd sequence a long time ago. For cos is 1 minus 1/2, right? I'm going to get an answer here in quadrant 2 and 3, and my reference angle is pi over 3, right? So cut pi into 3, or the whole thing into 6. So I'm going to get my answers at 1 pi, or not pi over 3, but 2 pi over 3 and 4 pi over 3. So theta 1, theta 2, 2 pi over 3 plus 2k pi, and for theta 3, 4 pi over 3 plus 2k pi. And there are my answers. I know I did those quick, but I'm going to recap it after test 3. Okay? I did those very quick.